All right, so what we're going to try to do now is a bit mixture of different topics. I'm going to start with maybe a case study and then of how AI was used in some contexts, and then we can look at it. Some of these you're probably quite familiar with if you've followed like how AI was used and maybe misused. And then let's see what kind of lessons we can learn, and then as we sort of take a mathematical perspective of like what learning is about, then we can sort of probe and see like where in applying machine learning techniques, what are the assumptions we make, and perhaps what are these assumptions that we make that are perhaps not very sound and we should be a bit cautious about. This is going to be a bit informal. I do not know what you're thinking. I don't know what your background is. If at any point you have an interesting comment you want to make, I want to hear your inputs. Feel free to interrupt as well. If you have questions, also just ask. And just so that I want to know like what you're thinking and like hear about a different perspective. My background is it's nothing to do with law. My background is all entirely in like computational side and optimization. So I have a very different perspective. I have sort of like to spend our time thinking about algorithms too. And in a sense, when people are a bit cavalier with the methods that they use, they make me a bit afraid as well, because like, do you know what's going on? And that's sort of like maybe a bit of what I'm going to get to today. All right, let's start with this. This topic about that. Sorry, am I allowed to step out of this zone or anywhere you want? Sorry, stand here. Okay, I'd like to move around. Let's start with this. This one. AI was used to predict recidivism. So let me be background. Over the past decade or so, like AI tools have been increasingly used to sort of try to predict or assess potential like recidivism risk, sort of the probability that someone like a past offender reoffends. Okay, and so this sort of tool or using like people's profile and try to predict what the risk of reoffending. It's not a new thing. It's been done before, and so I think. The historical methods were very, very crude, very simple. Just like just a few predictors, and they come up with a simple score, and there's sort of no science as to why these scores are accurate or not. But I think this came out a bit more prominently in like in the US with this case here. So some of the risk factors that they look at, like things like age, number of admissions and gender education level. Why do they want to get into this? The supporters say it's that like they help to reduce judge bias and errors. Of course, like anybody, a good salesman would say, this is something that sounds good. They probably just want to sell the product anyway. The critics is that these algorithms are proprietary, which is a bit sketchy, because you think about it, what they're saying is that like I want to protect this. I'm not going to tell you how I make my decision. It's a black box. This is protected, and they don't want to be able to have to say like this is the reason why I predict this person has certain risk. They just say like this is proprietary. I'm not going to tell you why, and I don't want to be liable for predicting like a risk for a particular person in a certain way. They don't want to tell you this. Okay, so if you're not happy with the algorithms, they're not obliged to tell you why it's that case. Okay, so one of the, I guess, the biggest story, if you look up any example on this, is this compass example over here. This is a software that was developed by North Point and used by the US courts. How this works is that you have to answer a 137 question survey. Okay, so it's an example of a survey over here. If you look up the website over here, you find like some people who work on this, they actually have a sort of entire survey. It's a lot longer. It goes a lot longer. Although some of these questions have a sort of repeated themes of group categories of like, broadly speaking, like past convictions, what kind of convictions that they have, family history, and as well as friends, whether they've have past convictions, substance abuse residents, and so on. One of the things here is that race, the ethnicity does not appear. Okay, they don't ask this question. It doesn't appear at all. Okay, so what happened was that like a public investigation went on, did this. What they reported was that like black defendants who did not recidivate over a 2-year period were nearly twice as likely to be misclassified as higher risk as compared to the white counterparts. Okay, so like somehow like white and black, same situation. The risk of a black person is somehow like a higher risk, assessed to be higher risk compared to a white person. The same is sort of for white versus black, it's sort of the opposite. Somehow they are assessed as a lower risk. And so you start thinking like, how do they do that? Okay, how do they figure out how they actually do this investigation? So the method's actually quite interesting. Okay, so what they did was that they went through like 10,000 records of criminal defendants in a place in Florida. There was a county where they had lots of data, so they could do it. So the idea here is that like you take all these past defendants, you take these 10,000 cases. They have two-year history, so they know actually whether they reoffended or not. So they know the answer. They know their profile. They know whether they reoffended or not. They put all the profile of these defendants into the system, the survey. The survey will pop out a number, the risk, either you reoffend or not reoffend, and then you look at the actual outcome, whether you reoffended or not. And so this is how they did this investigation. So what is surprising here is that like no point, like I said, ethnicity did not come out, right? So yeah. So but I think one of the criticism of this survey of this method was that like many of the questions that they asked do have some correlation with race. It's something that I think I guess we are now understand this a lot better. But I think when this came out, I think this was sort of like we were starting to understand like these are some of the problems that like using AI will have this sort of maybe unintended consequences. All right, so sort of an example that you will maybe get like a conversation going. Now, what I'm going to do next is sort of going to describe like the very abstract description of a machine learning task here. And I think it's also the faithful reflection of the previous example. And what I'm going to do here is that as we go through this process, we will then talk about like what are the implicit assumptions that are being made here. And if you want to, we will interrupt and talk about like how many of these are sound or not. All right. What does an abstract machine learning task look like? Okay, so broadly speaking, this task here, we can think of this as sort of like very abstractly as purely predict the risk that a person reoffends. That's all. Just predict the risk that the person reoffends, nothing else. The data set here is going to be a collection of historical records of past convicts. Their profile, that means the profile would be like all the answers to the survey that they would have put in. They did like so prior convictions, family history, and so on. Y represents a label. Y means like whether they convicted, sorry, they reoffended within the 2-year period or not. Okay, so this is the setup. And the idea here, at least the task that we want to do, is that later on, a new person comes up, so a new X comes about. He will fill in the survey with exactly some response, and the goal here is to predict why, whether this person will reoffend based on the data that we have just we now have observed. All right, so here's the machine learning task. A general machine learning task can be described as follows. The goal here is to find a function, a classifier here, which is going to be a function f. It's parameterized by theta. Okay, so you're searching for the function. The function should not be too complex. Okay, so we need to control some way of what kind of function. Okay, if you want to find a line, a very simple linear classifier line, then the parameters will be like what is the offset and what is the slope, that kind of thing. Okay, but if you want to pick more complex parameters, then potentially you can think of it something more complex. Anyway, we don't have to worry about that for now. We'll just say that it's parameterized by theta. Our goal here is to minimize the following error. Okay, so some loss function that ensures that the prediction, so f theta means like based on the model theta and the input x predict what is the outcome. Okay, make sure that pick a theta so that this is close. So what you want to do here is to ensure that the function, the prediction of the function closely aligns with the data that we observe. This is y. Okay, data is observed is y. Pick theta so that these two are well aligned. So the loss function here is a function that encourages us to pick functions that fits the data well. We're going to do this in average over the entire data sets, and that will be our objective. After you do this, so you do this minimization, you identify a good theta. Theta here identifies a good classifier that you're happy with. And in principle, this is the sort of the classifier that we report. And so later on, when you want to sort of like, when you create your own company that predicts recidivism, this is the software you come up with. Theta hat, just a new convict comes in, you compute this value and you tell them this is the risk. So in principle, that's how it is. And it seems to be a fair description of your problem. Any questions here? I think people want to ask. All right, let's go. All right, so what implicit assumptions are we making when we sort of like look at the problem through this framework? Are the assumptions we make, which of these are sound and which ones should be deserve some warning and be cautious, because if they fail catastrophically, if you're not careful. Okay, so this is sort of the theme here. All right, so maybe I want to start with some conceptual and modeling assumptions that you've made before I go into the maybe more technical ones. The conceptual problem is this, okay? So how likely is a person going to reoffend given the circumstances in the survey? Okay, so we're not looking to the future. So predictions can be incorrect. You have to be comfortable with that. And I hope people, so I think it depends on what you're predicting. You have to be understand that, like, I guess the predictions can be incorrect. You're not saying that this person will or will not reoffend. You're just saying that I predict that this is your risk, but I may be wrong, and you'll be comfortable with that. We're looking to also minimize the prediction error on average. If I can do 90% of prediction well, and I get 10% wrong, the 10% should not feel very unjust about it. It's just that my only goal was to do this good on average. Okay, so apologies to those that I've like assessed a risk wrongly because there are certain merits that somehow the survey didn't look at it. I don't want to be liable for that. My job was just to minimize, be good on average. Okay. So to be comfortable with that. All right, let's start with one. Okay, so what are some of the assumptions that are being made? The labels Y are indeed correct, objective, and free from other flaws. Okay, so the assumption here. Okay, so this kind of supervised learning setup where somehow like you start with the attributes, and then you say this person is like the predicted to have to have reoffended or not. You typically assume that the labels here are correct and objective and free from other flaws. Okay, let's see what happens if this what happens if you are not too careful about this. All right, so this in 2018, Reuters reported this, like Amazon had this secret tool that they use for hiring, which they didn't actually tell you. But it's only reported when some people in Amazon spoke to Reuters about this. They only knew about this when it was shut down in 2018, around that time. Okay, so a few years ago, step backwards a few years back, Amazon started using automated tools to perform screening. Okay, so the idea is that like you submit a resume to them, there was some way to screen a resume, and then they would sort of predict and say like, okay, among this pile of 100 resumes, you should look at these 5 resumes. These are the top candidates for this job. The rest just ignore. Okay, so Amazon had a lot of like, they want to do a lot of huge volume and not just send huge volumes of parcels. They also want to like, I guess they want to hire quickly as well. Right. So that was the idea. About 2015. Okay, so it's sort of some of these ideas here. I think a lot of these we were very comfortable. We understand this very well. But 10 years ago, many of these things were we sort of overlooked this. Okay, so it's a bit. Okay, so in 2015, what happened here? And Amazon realized that like a year later there was a problem with gender, and like somehow the recommendations did not appear to be gender neutral, and it sort of appeared that like because they were getting a bulk of the applications they were getting were all male, a lot of males, and like and somehow they were sort of like they realized that the algorithms were sort of predicting like if there's any sort of like mention of the word women or female, they would sort of give it a negative score. And sort of somehow like in the sense, Amazon, the automated hiring tools was actually unintentionally learning the biases that had already been ingrained in some data sets. So if the hiring practices in the past were already biased to begin with, the algorithms were also automatically learning the same bias. It's not the fault of the algorithms, it's that the data sets were sort of like had this problem to begin with. So yeah, so if your past data examples were biased to begin with, then you should be confident that the algorithms will also learn the same bias, the same discrimination as you did. So we understand this a lot better now, but I think 10 years ago, we were a bit shocked when these sort of things happened. Next one, algorithmic bias. All right, we minimize this objective over here. All right, so let me give you the sort of the prelude here. So in this objective over here, we form this objective by looking over the data samples that we have. Okay, so these are just a finite data points. These are the samples that we have. Use it to train a model. It is in the hope that in training this, in obtaining a good classifier here, we hope to do a reasonable job on new examples that we have not seen, right? We have not seen this example. We have no idea what this is going to look like. So in what case, how can we justify somehow that like, based on the data that we have, we can actually make some conclusions on data that we have not seen. How can we talk about this? So this is sort of a question here. How is this a justified assumption? All right, let's be a bit more precise. Let's just say that all possible examples of data can be described by some distribution calligraphic P. So this P on top over here. All right, so this is sort of like a theoretical construct. Just think of this as like, for example, the distribution of all possible X offenders that we'll ever see. Okay, so something that might exist. Okay, think of this something in our head here. And so ideally, if we could actually describe the entire universe of all possible offenders, then the real problem we want to solve is this thing over here. We want to minimize the error with respect to this distribution of all possible X offenders. Right, this is the ideal machine learning problem we could do. If you could do this, then you're sort of done. Everyone will be quite satisfied with our job. Now, and this is impossible because we cannot know anything about the whole universe of all possible X offenders. So this is out of the question. So what people do here is that like when we minimize this function over here, this is with respect to the finite data points. This is somehow we use this as a proxy to this problem over here. Yeah, so the question is like, when is this an acceptable proxy for this thing here, which you have no idea what it looks like? Yeah. So that's the question, like, when is it the case here that like the answer you get here from this problem is a reasonable approach to this problem that you cannot have access to? Sorry, question. All right, maybe it's not a simpler question here. Is it the case that a data set that we have over here is somehow representative of all the possible X convicts we want to see over here? Okay, what do I mean by this? All right, so here's another different example over here with facial recognition tools. So again, I think a lot of these lessons that we learn now, we know it better, but I think it was when it first came out, it was a bit, how do I say? was shocking. I think or like surprising that like this could have happened. Okay, now we're a lot more careful about this. All right, so in the earlier years when facial recognition tools were starting to gain adoption, it was reported that like a number of studies that like on these tools that like they tend to perform worse on people of color than on white people, and also tend to perform worse on females than males. This is somewhat problematic, okay, depending on which country you're talking about. Like, but I think in some of these countries, maybe the US, they were actually using facial recognition technology to make arrests sometimes. Okay, so if you use it for like authentication, maybe that's one thing. But in the US, I think the reports that some were saying that like they use like from CCTV, they could like use this to like identify people that they will later then make arrest. And so somehow like error rates here have like can have a disproportionate impact on certain people of like of color, and this was a problem. Okay, so one of these studies here was that was initiated was called Gender Shades by these two authors, and this was released in 2018. All right, so what did they do? All right, so this was the way that they tested, or like how they show that these facial recognition software was a bit problematic. Okay, so what they did here was like one of the, I guess, the biggest contributions here was that they released a curated data set here that's meant to be inclusive. They created a huge data set of many like photographs of people over here. And the idea here was that they want to create it in such a way that people of colors and all different countries were all represented proportionately. Okay, so they were quite careful with like the people from different countries, how they look like, and they make sure that the data set does have the sort of like the proportion of the people in the data sets was actually a accurate representation of the people in the world. Okay, so that's sort of the idea I did, as well as like gender as well. Okay, so this is the data set that they came up with, and it's something that they released it publicly so that like people could test it and use it for training as well. All right, so anyway, now they've gone ahead with creating this inclusive data sets. They went ahead and tested on the accuracy of the facial recognition software in these examples. All right, so these were the results that they did, and it looked at, I think, a couple of like facial recognition software. These were results that reported at the point of time. Of course, these people definitely have gone on to fix it and rectified all these errors here. So these errors are not true anymore. Anyway, what are these results going to be about? So on this series, talking about just race or ethnicity, sorry, skin color, darker subjects and lighter subjects accuracy, lighter subjects close to perfection, I guess, for at least for Microsoft. Darker, much worse. Here you see the error rates over here, so about 10 to 20% over here. On this on the right-hand side here, they did on two axes, both on like skin color as well as gender. What you noticed here was that for lighter male, there was close to perfection. There's basically no errors, and whereas for like people of color and then especially females, it was much worse here. So it's a bit shocking here. We went from 100% here to like 60%, so like 2/3 as well. If you think about it, what's going on over here was that like if you sort of think that your technology is very mature because you're reporting these numbers here, and you might think actually the technology is quite mature because you've like close to perfection over here. In reality, like there's this sort of people that have not really tested on because they don't really appear in the data sets. This was the sort of the true performance on data that you sort of neglected. All right, so yeah, the software tend to perform worse on people on women and on people of color. So what was the problem over here? And I sort of go back to this assumption over here. It's that one of the known problems is that like the data sets that they've been training on at the point of time, not anymore, was that the white males were typically overrepresented in training data sets. So like you go back to 2015, 2018, if you go to Google search and find out the training images, tend to get more white male examples as compared to female or people of color. Right, so this was the, so going back to this assumption over here, like somehow you were assuming that this data set that you have here was was actually representative of the data that you do not see here. This was simply not the case over here. All right, so in this case over here, the sort of the technology itself, okay, the algorithm wasn't doing anything wrong. It was actually doing something legitimately optimal. It was doing something optimal. It was optimal to this criteria over there. It's just that the criteria that they have was that like there were a lot more white people and white male, and so it was optimal, but like the notion of optimality was not what we want. Okay. Right. So yeah. So anyway, since then people have sort of corrected this. So there are, I guess, simple ways to fix this. Either you make sure that the data set that you have here actually represents each of these pockets of the population in the correct way, or perhaps you can weight the data sets differently so that you get the correct outcome that you want. Oh, sorry, I just want to say here. All right. Through this bit, we are ahead of time actually. All right. Any questions? All right. Okay. So this is good. Let's see. Okay. This is going to be a bit heavy. It's probably perhaps best for grad students and they feel like they lost. Apologies. All right. So statistical assumptions over here. All right. So let me tell you a little bit something about learning theory. So it's more mathematics from now. Okay, fine. Let's assume that this data set that we have here is indeed representative of something that's unknown. Okay, so a huge assumption here. Somehow we are assuming that this data over here that we have is actually an accurate representation of something that is unknown. And this is really a huge, massive assumption because you never know what you're going to get in future. Okay, so what I'm going to do in the next few slides here is to tell you something very classic in this statistical learning theory, which is that actually it's possible to make some comments about this. Okay, so how can we say that the answer that we get here on finitely many data is somehow a reasonably good estimate to the solution that we have at the bottom? Okay, how can we say this? Okay, so this is the sort of the machine learning algorithm is doing this. I work with the data set I have. I want to give some estimate. I want to say how well it will perform on the data that I've not seen. That's a goal. Right. Okay, so this is known in the literature as statistical learning theory, right? That's how we, okay, so let's assume, okay, so this is the data set that we have. We'll make a huge assumption. We're going to make a huge assumption here with this that the data set is somehow drawn from a larger distribution comprising all data set that one might possibly encounter. All right, so it's a huge assumption. So let's imagine what's happening over here. Personally, I don't agree with this assumption, but if you don't make assumptions in mathematics, you will not make progress. Okay, so imagine there's a whole universe of all possible ex-convicts or convicts or whatever people that you might actually see in future. So from now to the end of time, there's all these people that sort of pop up in here. And somehow that the data set that you have over here is obtained by randomly sampling this sort of community of people, okay? And if you sort of sample from them uniformly, okay, and so the data set you get is actually obtained by sampling from these group of people uniformly. So how much everyone has an equal chance. I pick one guy, it goes to my data set. Uniform chance, I pick another one, goes into my data set. So somehow I'm assuming that this data is how I get this data over here. Philosophically, you might not agree, but that's one thing. The next thing over here, how do you formally say that or quantify that a solution or classify it? Okay, so the F theta hat here is a classifier that you come up with. That means like the software or the software for predicting recidivism. That's you want to say how good it is. What do I mean by how good it is? Okay, in the ideal case, you want to obtain something that minimizes this objective. Okay, what is the objective over here? Okay, this is this is a classifier that minimizes with that it performs best on all data sets, the entire possible data of all ex-convicts that you might see. Okay, so this is sort of the ideal case where you suppose you can see all possible people, and this will be the objective that you have. Okay, this is impossible. Okay, instead you have to somehow look at this. Sorry, I'm repeating myself a little bit over here. Yeah, so in principle, we only have finite data, so we get this f theta hat here from finite data, and we want to say how good this is. All right, so how do we say how good this is? This is one way of measuring how good the classifier that we have f theta hat is. We do so by comparing the difference in the loss over here. Okay, this is a bit of mathematical expression, and I understand that some of you are not, when you sort of see this, you might freak out. Let me tell you what this actually sort of means, all right? Now, the left-hand side here is the performance or the error. Okay, so f theta hat here is the one that you get from your algorithm. This is the one that you obtain using your machine learning algorithm using finite metadata. This is the data that you have. This here is the performance. Think of this as the performance of your software, your algorithm. This here is the performance of the ideal classifier. That means if someone could magically see to the end of time and look at all possible human beings, this would be the best answer that you could possibly get. All right, what is this difference over here? This is the difference between the performance of these two guys over here. Now, on what are they being evaluated on? All right, so these two algorithms are being evaluated on the performance on classifying on all possible people that they might see. So actually, this is sort of like a, let me say this again. They are how they're being evaluated. They're evaluated on all possible like the entire universe of possible ex-convicts. So this is a huge all possible outcomes that you can see. All right, so what can you say about this? Okay, this is the ideal case. So this is always going to be the winner over here. What you want to say is that somehow this value is small, so, which means that the performance of the machine learning algorithm is somehow almost as good as the ideal classifier. On what? It is almost as good on all possible instances. That means like even including all those that you cannot see, but could possibly see. And so this is the how you can quantify how good the algorithm is. Right. So So the remarkable thing about this is that this is actually possible to make statements about this. I will state the theorem. And then we will talk about the consequences, or like we will try to parse what each of these statements actually means. Now, number one, suppose that the hypothesis class is not overly complex. Okay, hypothesis class. Okay, what does this mean? Okay, so hypothesis class means the kind of functions or classifiers you look over. For example, you might look at all very simple classifiers, maybe like they're just linear models. There's one type of classifier. Maybe you look at things of curves of this sort of models. Maybe a bit more squiggles, that's fine. Suppose that it's not too complex, okay. If it's not too complex, then that's good. Okay, so formally, suppose that the VC dimension is finite. Ignore this. Okay? That's not important. If we learn enough data samples, and so there's some value of it. Suppose that we learned like a good model using a certain number of samples, then we can guarantee that somehow our learned model is good in a certain sense. Okay, in what sense is it good? It is good in the sense that compared to the perfect classifier that you cannot get to, the perfect classifier, you are only going to make an epsilon like a fraction of errors. Okay, so this is what let's say epsilon's number is up to you to pick. Let's say you want to pick epsilon to be, let's say, 1%. You can somehow guarantee that like if you pick if you have enough data points, you can guarantee that the classifier that you learn using an algorithm is going to be 1% worse than the ideal classifier that you cannot have access to. On what? On all possible data. That means like all possible data that you might actually care, that they would care about, with a small probability 1 minus delta. Okay, so let me go to that in the next bit over here. All right, so maybe some remarks over here. I'm going to do this slowly. First, what is most surprising about this is that we can actually give a guarantee of the performance of our learn classifier on all possible data. Okay, this is quite remarkable because all possible data, that means the data, including data we cannot see. I have no idea what the data looks like. I have no idea what a new X-convict might look like. I have no idea what new examples will look like. Nevertheless, I can even make a guarantee that I will be like this good or this good to the ideal classifier, despite the fact that I have no idea what this new data set new data point looks like. Okay, so it's quite remarkable because I can talk about things that I don't even know what it looks like. All right. Second is that the distribution. So how is the data points? How do they show up? Somehow this actually never shows up in the theorem. So like never says that the data set contain diverse examples or unequal representation. Doesn't care. And somehow that this doesn't seem to care about this. Third, there's this technical condition of this appearance of this probability 1 minus delta. It's a bit technical here. So this is sort of like to do with the model. Somehow, like we are always assuming that like there's this universe of all possible X-convicts, and the data is obtained by just like I sample from this guy. If I'm very unlucky, I might be picking like very poor examples. I might pick like certain pockets of the population. If I'm really unlucky, I might be like picking from the same population, like maybe like a same group of people multiple times, and I ignore other parts of the population. I could be very unlucky, and in that case, the algorithm does not work well. Okay, so there's a very small chance that the algorithm does not work well, but in general, this probability is small. Right, next one. Okay, so this might be a bit useful from practical views. Okay, so I did mention something about the how complex the class of the function class is. Well, this is a theoretical definition. Okay, so I did mention this something about this complexity here. This is a theoretical definition, so one should be a bit cautious about reading too much about what the number says. Okay, so transferring something from theory to practice, you got to be a bit careful. But I think in one case here, if that like if the complexity says that it's infinite, then you should be a bit careful. Okay, so if somewhere along the way, if you've been told that the complexity class is infinite, and this can happen, and it's a warning sign that you might be looking at a function class that is too complex. What does it mean by too complex? If the function class is too complex, it means that your model has the potential to memorize everything and actually learn nothing at all. So it's possible like that if a function class is too complex, you're basically just trying to memorize the data points and you actually never learn any intrinsic patterns. Okay, so this is something to watch out. But other than that, I think you're okay. All right. All right, okay, so I'm gonna give you maybe one punchline. Seems like a very technical result over here. Why should this be true? How can I actually say something from finite data to infinite data? I'm just gonna give you one quick analogy here, and that may be your only mathematical take-home point for today. And it all comes down to this thing over here. Okay, it's about coin tossing. Okay, let's start with this picture over here. It's actually this is a technical result over here. Things inequality over here. Let's toss a coin, all right? You toss a coin like a fair coin, let's say 1,000 times. How many times do you expect numbers to be hit? Half the time, right? Okay, but you're not getting half right exactly. You're not going to get, let's say, 1,000 times, you're not going to get half the time, you're not getting exactly 500 hits. But you should be getting quite close. I mean, I don't think you're going to do it right now, but if you try it on like a computer program, you should be quite close, right? You shouldn't deviate too far away from like half, 500. Okay, if you do it 1,000,000 times, you should get even closer to like half as well. So like the fraction here. So as you do it more and more often, you should get a number that's very close to 50% of the time. Right? Intuitively, that sounds correct. Right? In fact, we actually have a very precise result here that controls or tells us what is the probability that this number deviates from half as a function on it. So let's say like if I put it like if I toss a coin 1,000 times, it's an estimate of how unlikely is it that you get a number that is more than 50.5%, for example. If I do it 1,000,000 times, there's also another number here that tells us how unlikely is it I'll get more than like 50.5% hits, for example. So there's a number over here. This is called Hooftings inequality. Okay, so how does this relate to our result over here? How does this connect to what we have? Okay, so somehow magically this idea of this machine learning task here has somehow a hidden coin inside here, which once you draw the analogy to coin tossing, then we can see the connection and actually make conclusions about things we can, about the true distribution. Okay, how do we see the coin? Where is the coin? That's a question. All right. Look at this objective over here. This is a loss function of fx and y. Okay, what does that mean over here? Okay, so this is example over here. X is an example of a person, an ex-convict. The profile, if using a survey, that's X. Y is the prediction whether it whether it reoffends or did not reoffend. So it's a number. It's like either 0 or 1, reoffends or did not reoffend. All right. Loss here is the it's just like the difference. So in other words, the question is, did I predict this correctly or incorrectly? Okay, so F here is it's sort of a model. F is any model that you have or classifier. So you take a survey, the F here reads the survey and says, okay, I'll look at this profile, and then I decide, okay, this guy or this person, I'm going to say the risk of reoffending is 90%. That's a number. And then maybe maybe I said reoffending is 1. So I just pick 1, and somehow like my prediction is either correct or incorrect. Okay, so my prediction is either correct or incorrect. Okay, so the loss here represents like the outcome of my prediction. It's either correct or incorrect. So it's 0 or 1. So that's sort of the coin. Okay. Then what's happening over here is that like I've always assumed that somehow there's this universe of ex-convicts that we are sort of drawing data like example from. The action of drawing one, okay? So this is like as though we were tossing a coin. So this action of actually like observing this person here is like drawing a coin. In a sense, the ideal objective we want to minimize is this thing over here. This is the what is this? This is the like the loss here means like our performance on a single person. Then we take the average over the all possible people in the entire universe. This is what this statement over here means. This can be viewed as the average performance of an algorithm or function f over the entire universe of all possible people. All right. So somehow there is there. So this like the fact. Okay, let me connect to this. So every time we draw a person, we are sort of like taking drawing like a coin flip, and he has a certain weight. It's a bias. It's like think of it as a bias coin, and if you flip this coin enough times, you should get an estimate of what the bias is in that coin, and that's the idea. Even though there's a true value which you cannot access, if you flip this coin often enough, you have a reasonably good estimate. Okay, and so basically what I want to say here is that somehow, if you think of this analogy of coin tossing, then this objective here is actually a reasonably good approximation of this thing over on the right-hand side. And once you make that mental connection, then you sort of see and can believe why that like by minimizing the left-hand side objective, I should be actually doing a reasonably good job on the right-hand side objective. That's the idea. Yeah, that's all. So if anything you get from today, if anything, anybody asks you about statistical learning theory, you can tell them it's down to the sort of analogy of coin tossing here. Once you sort of think of it as a coin toss, then that's the main idea. Right. Right. So I think when giving these talks, you cannot give a lot of technical stuff at once, but you lose people. So I'm going to like divide in chapters where like if you get lost, you can come back here with a different example over here. Let's see. Something fun here. How much more fun stuff do I have? All right. Okay. Some fun stuff over here. Minima. Okay. This is something that like I think like for me as an optimizer, it might make more sense, and like maybe for a practitioner, it's something that it's easy to overlook. Okay, maybe minima. All right, complex models. So this is something maybe not have a good sense of the question. So I know what people's background are. Here's a question, like when fitting with a model, what do you think about? Is a complex model better or not so good, right? How do you know if the model is overly complex? So this is a question. If a model is a bit too simple, then perhaps we're just not very good at classifying to our cases over here. And that's a problem, it's not good. On the other hand, if it's overly complex, then it just might be memorizing data points and it just doesn't actually learn anything useful. So how do we know it's complex or not overly complex? Well, what happens in practice? Okay, in practice, nobody really cares actually. And so the way they evaluate here, whether you like it or not, is called a test error. Okay, so I have a data set here. I partition some of these to be the test. I don't use it on training. On one side, I do training, and then I will say, hey, how about you perform on the data that you did not see? And if somehow you're doing quite a good job on things you have not seen before, then somehow I will say that like you're doing well. And so somehow at this point of time in this discussion over here, we don't really care about like how complex or not complex the model is. And so long as it does its good job on test error, we don't really care. And how it is. All right, and so let me give you some fun example over here in 2016, around this time here. Neural networks. How much capacity do neural networks have? Let's take a neural network that is known to classify images quite well, pretty well. Let's say a 10% error. Train a data set with correctly labeled data, and they train a pretty good network, and it's able to classify data into different categories quite well, and seems like it works well. Now, they repeat the same process again. Now again, they start again from scratch, but instead of giving the actual correct data set, they give garbage data. Same images, different labels. Okay, so what's this data set over here? So these are like data sets of like maybe like 1,000 or a few thousand data points, and each of them is a label. Like this is a car, this is a cat, this is a dog, or something like that. It's one of these like 10 or 50 categories, and the idea, or I think 10 categories. And the idea is that for every image, you have to correctly predict the label. Tell me what it is, and your answer can be 1 out of 10 answers, and you have to get like you have to tell me what the correct answer is. So that's a question. There's only one correct answer for every image. And so what the researchers did here is that like instead of giving the correct answer, they give the data set where all the labels are all complete nonsense. And so there's actually just complete garbage. The data set is just entirely garbage. So what happens over here? So what I noticed here was that shockingly, when you put into the neural network, they realized that it trained with 0 training error. Okay, so somehow like even though you give it complete nonsense, the neural network is able to memorize all the data points correctly, even though there's no inherent pattern. Okay, so the thing here is that these neural networks here have tremendous capacity and can describe very complex patterns over here. So somehow like you can memorize patterns that are interesting to us, they can do correct prediction, but the same architecture, like somehow if I sort of get to train on different garbage data, you can also memorize total nonsense as well. Yeah, so this was something that they did over here. Let's pay attention to the right-hand side of this diagram over here, where this is our label corruption. So with no corruption, okay, the test is test error. That means like how many mistakes are you making on the data set they have not seen? Okay, there are 10 labels. So if you are doing random guessing, you get 10% correct with pure chance. So if you're here, you're doing a terrible job. You're just guessing, right? And so what they noticed here was that like if you just randomly mix up all the labels, you're just doing rubbish. And so this is sort of what they expect. But when they were not actually giving true labels here right at the beginning, so these are all the labels are perfect, these models were actually doing a good job. They're only getting 10% error. So they're actually sort of like these models had the capacity, had the ability to learn well. There's so much capacity to learn well, and at the same time, the same models can also learn complete nonsense as well. So this was something we noticed over here. So I'm going to skip this over here, but maybe this question I have here, like I don't quite understand here, which is that like what are neural networks doing? They have the capacity to learn a lot of stuff. They can describe very complex patterns. So how is it that somehow these neural networks uncover like learn these data points? Is it because like neural networks are special and they are good at identifying patterns? Or is it that data itself is very structured, it's very low complexity. There's structure and data here, whereby if I take any reasonable method, including machine learning, including neural network, I would have actually learned these patterns pretty well anyway. And it's not that the neural networks are special. It was that the data itself was actually very structured. And if I take any other method, probably I could have done a good job and maybe get good classification error. So this is a question here. I think I'll stop here. Maybe I'll have some homework over here. What I will try to do here today was talk about like assumptions that we have made. I'd like to think about maybe think about, maybe go back again. Tell me this tomorrow, which is that in the practice of law, as we apply maybe in this sort of machine learning or AI techniques here, what assumptions do we make? Right. For one, I think I should warn you here. Do not simply trust what a computer scientist tells you. Like I tell you that you want to minimize this as a loss function over here, right? This is what I know how to optimize. The reason why I choose to do this is because I have good algorithms for minimizing this particular loss function. But you yourself, you have an objective here in your head here that is very different from what I have. Okay, the objective that you have here does not necessarily, when you try to translate it into a computer algorithm, that might not be what you're seeing on over here. So you need some communication with someone am I actually faithfully translating the conceptual problem? What am I trying, what's the real sort of conceptual outcome here that I want here? And did I actually sort of faithfully represent this in terms of the computer algorithm that I'm solving here? And any other assumptions that we're making, I'd like to hear about it and we can talk about it tomorrow. Stop here.